Jenny Grosslight, here to introduce Agilent's new U4154A 4 gigabit per second state mode logic analyzer, capable of capturing signals with data valid windows as small as 100 picoseconds by 100 millivolts at the probe point, providing you the highest confidence in measurement accuracy. Our target for this demonstration is a DDR3 desktop operating just under 2 gigabits per second. This is the U4154A overview screen. The leftmost icon is the probe tool that shows how to connect your specific probe to your analyzer pods. The module icon represents the U4154A. There are three icons where you control the mode settings and the trigger. The DDR decoder is found under the Tools section. We have three viewing windows. One is a listing window off of the decoder. There is a state waveform window and a timing zoom window with high-resolution waveforms around the trigger point. Opening the state waveform, on the left we see an activate, then 4 valid read requests back to back. On the DQS line, we can see the preamble followed by the 4 back-to-back bursts of data, and we can measure the CAS latency between the first valid read request and the beginning of the data strobes. Notice that the logic analyzer triggered at the end of the fourth burst. The U4154A is unique in its ability to trigger on sequential events at 2.5 gigabits per second. In the trigger window, we see that we were looking for a valid read, followed by the CAS latency measured in samples. Then on one single sequencer level, we are looking for a burst of 8, inputting the exact pattern of interest. If that pattern is found, we go to the next step. If not, we go back and look for the next read, followed by a second burst of 8, a third burst of 8, and then when the fourth back-to-back burst of 8 was found, the logic analyzer triggered. In the listing window, we have 3 extra labels created by the decoder: the physical address and the actual DDR bus decode, where the valid read command information includes the row address from the activate, the column address from that actual read or write command, and then the data associated with the command. There's also a cycle type that lets us know what type of command is being executed on that particular sample. We can scroll through the entire listing and see our particular back-to-back burst that was captured, and all other data for up to 200 meg deep around the trigger point. Moving to the timing zoom window, here we have a high-resolution capture of all signals on the bus. Of particular interest would be each strobe with its associated data byte, where we can observe the flyby routing. To understand how the U4154A provides the highest confidence in measurement accuracy, we open up the Thresholds and Sample Positions window from the Sampling tab. Observing the read data bit by bit, these eyes are a composite of all valid data in a read burst. The pixels can be as small as 5 millivolts by 5 picoseconds. The U4154A has unique sampling hardware and software tools that provide the eye scans of only the valid read eyes and write eyes on each signal. We are viewing the read eyes. Scrolling through the data, we can observe the signals relative to each other for quick signal integrity insight. We get all of the signals in the system. Here between bit 7 and 8, we see a byte lane shift, which is expected. Note that almost all of the eyes are relatively the same size. That is, at least for the first 2 byte lanes. When we get to the third byte lane, the eye is relatively smaller than for the other byte lanes. The eyes are large enough to capture accurately with the U4154A. This is signal integrity insight that lets us know that byte lane 2 does not have as open of eyes as byte lane 0 and 1. Scrolling down through the data until we reach the strobe eyes, we see that relative to each other, strobes for byte lane 0 and byte lane 1 are relatively the same size. DQS2 has considerably more noise. To verify the signal integrity of DQS2, we would use a high bandwidth scope and high bandwidth probing. This concludes our overview demonstration.